Aaron, Jonathan, great to have you on the Bio Breakthroughs podcast. How are you today?
Great, thanks.
Doing awesome, thank you.
Let's dive right in here. I did not have the opportunity to go to this event, which hopefully I can go next year. But at DFARM 2024, Aaron discussed the next generation form of artificial intelligence, Causal AI, and how it can optimize clinical trial feasibility assessments and trial sponsors and determine the next best course of action to keep trials on track. Can you provide a high-level definition of Causal AI, and how does it differ from generational AI? I mean, I think everyone's familiar with ChatGPT at this point, so would love to hear that.
Exactly. And I think you've just made up a new term, Causal AI, it's actually causal.
Oh, causal. Oh my.
Causal as in cause and effect. But Causal AI, that also sounds like something we should invent soon. So maybe that'll be a different podcast. So causal AI and the distinction between generative AI and more sort of causal approaches to machine learning and statistics is that Chat GPT and other generative models, they're trained by essentially observing lots and lots of different data sources. Where Chat GPT, obviously, text, English language, human language, I would say overall, and then some people would say that Chat GPT is something like a very highly trained parrot, right? It can repeat things it's heard often. It can synthesize some new things, but it doesn't have any real understanding about what the underlying sort of basis of those of that content. It is for content generation. You can ask it questions, and you can ask generative AI to propose hypotheses, and it can do that. It can propose many different hypotheses, some of which are reasonable and realistic, and some of which are complete utter fabrications. So that the so-called hallucinations that people talk about. Causal AI has a very different bent to it, and it is all about trying to understand. We have observational data, but not only is it just something that we can observe and parrot, but we want to try to make sense of it. We want to say there are some inputs and there are some outputs. There are some results. There are some outcomes. And those outcomes are things that not only do we want to predict them, predicting the weather, predicting the election, those are predictions that you can make. And we can talk about, whether your predictions are accurate or not. But for causal AI, it's not just about making predictions, it's about understanding why. What are the underlying root causes? And that's where the sort of causal AI comes from. What are the underlying root causes? And if I make a change, if I make a perturbation, if I go into the system and I turn that lever or I flip that switch, then not only predict what the outcome is going to be, but help me understand what is that outcome in that particular very specific situation. And for clinical trials, this is really sort of important. We talk about making trials more efficient, more effective, cheaper, faster, stronger. And all of this is about saying, well, we have some operational plan. There's plan A and there's plan B. Well, what are the differences between plan A and plan B? Those differences are, again, these sort of operational levers and knobs that we have to manipulate. So causal AI gives us an ability, a capability to make kind of real world predictions about what some of those changes are going to yield as outcomes.
Yeah, and if I can just add to that as well, I think Aaron summed it up really neatly. But one of the key things, if you think about how we use it within research and development today, is we focus a lot on feature importance and what features are really providing the predictive index, as Aaron mentioned. What's most interesting that I like about causal AI, or casual AI, I like casual AI now, this is my new thing. But with causal AI, what I find really interesting is the fact that if we keep leveraging the standard machine learning techniques that we have today, the chances for us to create spurious correlations are a lot higher. And that's one of the big issues as well, is that, the cause and effect, as you said, sometimes what we see between, let's say compound A, patient B, are not necessarily directly connected. So it looks like it with some of the data that we have today and with some of the kind of fundamental machine learning techniques that we have. However, if we start to use causal AI, we actually start to understand a bit more cause and effect, as Aaron said. And one of the things I really like is the Spurious Correlations website. If you haven't seen it, go look at it. It's fantastic. There's a great thing about I think it's the distance between the moon and Uranus is exactly the same correlation as the amount of energy generated by Japan, right? Completely irrelevant, but it does look like they're completely related, and that boils down to a thing called compound and compounding within data. And I think something that's very important for data scientists and senior leaders in R&D to be aware of, that maybe this is not necessarily directly linked, and there could be a middle player in the middle. So what are those middle players? And as Aaron said, those perturbations that we might change and lead to impactful decisions, impactful information that we would have within our system.
I want to hear from both of you, and we can go back to Aaron, and then we'll go back to you, Jonathan. But how can causal? See, I got it right there. It's amazing. You you mix those letters up when you don't have that coffee early enough. So how can causal AI improve clinical operations? Aaron, we'll start with you, and then we'll kick it back over to Jonathan.
Sure. So, just picking up where Jonathan left it, right? Those hidden variables, that what we call confounders, things that are in the system, and maybe we know about them, but maybe we don't even know about them. They could be, completely hidden, but whether they're observed or hidden, it's very easy to see connections and to try to make sense of them. They're sort of the human logic steps in. So, for example, eligibility criteria, something that we think a lot about in terms of the overall design of a clinical trial. Who are the patients that are most likely to respond to this particular therapy? Who are the patients that have the most unmet medical need? What is it? Let's sort of describe very explicitly what exactly are the criteria in which we're going to select the patient cohort that's going to participate in a particular trial. And one of the very common practices is to say, well, we're not the first person to ever run a clinical trial. Let's look back in time, and let's look back through the clinical record and see what other trials have been run in this particular indication. What was the eligibility criteria that they used? And when we look at sort of a dozen so different trials, there's going to be some differences in those eligibility criteria. Some may be stricter, more narrower. Some may be looser, more wider. And it's very easy to start building up a sort of a hypothesis, a story that oh well, trial A had a very fast recruitment rate, and their eligibility criteria was actually much wider, and so therefore we should also have a wider eligibility criteria, because we would like to have that same fast patient recruitment rate that we saw with study A. And in fact, maybe we won't just base it, because we're good statisticians, obviously, we're not going to just base it on one study. We're going to look across those dozens of studies and compare the different eligibility criteria and try to make sense of what that is. And again, this is all very rational. And you say, oh, look, these, out of those 12 studies, maybe, just to simplify, 6 of them were strict and 6 of them were loose. And of the 6 loose ones, 4 of them were fast. And of the 6 stricter ones, 3 of them were slow. And so that looks like it's, roughly correlated. So let's, just again, to be kind of hand wavy, then, let's try and go after that. But, we don't always have all of the information. And what causal AI, causal machine learning gives us is the ability to say, well, great, we can see that correlation exists, but what other explanations could there be? What other, again, either observed or hidden confounders could there be? Maybe the trials that were faster had a patient registry behind it, or some other advertisement campaign that was more effective at reaching patient populations. And in fact, it had nothing to do with the eligibility criteria. So there's just one kind of tangible example that you can kind of paint yourself into a corner with correlations that make you think. And again, they sound real obvious and they sound understandable, but in fact, if you end up then making that choice and not seeing the effect that you want, you loosen your eligibility criteria, but you still have a slow trial. Now you haven't gotten the benefit, but you've given up a particular cost.
Yeah. I think, it's a great point, Aaron. And I think the other piece as well, if you think about a lot of pharma companies now are trying to focus on where are the patients. And so it's a very simple paradigm of we have these sites in this location. We know there's 1,000 patients around the site. The reality is when it comes to the crunch time for recruitment, that doesn't show up or that doesn't, directly correlate. And then everyone sits around scratching their head saying, well, the real world evidence told us this, and we actually don't see it. Having a much more holistic approach across and joining a lot of data sets together and being able to leverage all of that within this type of model, I think is where we'll see a dramatic difference, not just from inclusion, exclusion, and study strategy and protocol development, more even into the operational side when we start to look at participant recruitment and using that data to help us identify how can we actually operationalize in a much more effective way. And in the reality is if we can do that, that will help us really accelerate the time lags that we see in clinical research as it is today and has been over the last 10, 20 years.
Now, I want to make sure we have, we also talk about, there was an ISR report that was talking about almost 80% of clinical trial feasibility assessments have poor data collection mechanisms for comprehensive estimates and reliable forecasts. And as a result, that makes trials slow, resources are wasted. Can we talk a little bit more about how causal AI-based technology could help in this particular instance?
One of the key things that I find quite interesting on this is this 80% value is thrown around quite a lot in terms of delays. Every measure that you see where there's a problem in clinical research is generally about 80% for whatever reason. So I'd love to actually use causal AI to understand where this metric is coming from in a lot of research. But one of the key things, as I was saying earlier, one of the key things that I think for us is understanding that nuance of all the data that's actually around. And so for around a clinical trial site, clinical trial, and for me, I think one of the key things is actually the strategy, the build at the beginning. The strategy is what's most important, the inclusion, the exclusion, and the impacts. And for us, if we look at this from an operational identification, site identification problem, that I think really trying to understand, have we got what the impact effort is across the different inclusion exclusions, because we are starting to see, particularly if you look at oncology indications, we're getting much more narrow on and much more focus on different patient segments. So those inclusions and exclusions, I think, carry a much bigger weight, but because we don't understand the nuance between them and the relationship between them and that confounding aspect, that it actually makes it very difficult. And we're just like, oh, well, this is what we expected and it didn't show up. The other piece is I think there's actually hidden data in there that we haven't realized is related. And I think causal AI will help us understand that. Because if you look at it, recruitment techniques and forecasting generally has been quite poor over the last 20 years. There are several tools and gold standards, and probably 1-2 gold standard tools that we see across the industry. So what that tells me is we have something that works roughly, and we have different pharma companies adjusting it to make it work to suit them for their enrollment. And Aaron's smiling, so I think he and I have discussed this before. But I think what's interesting is if we could actually leverage this to understand and build out a graph visualization of what are all of the impacts and how are they impacting, I think that will help us give us a much greater insight as to what are the real driving factors in this recruitment. So we move from this bathtub Weibull distribution to something that might be a bit more reliable and consistent that can help us plan in a much more effective way.
Yeah. So I mean, I guess all I would add to that is, the old quip about, making predictions is really hard, especially about the future. I think the fact is that when plans are made, those plans are always by nature optimistic, right? And so 80%, 9% of trials end up being late, delayed in some ways, don't meet their targets. I think that is a sort of natural consequence of the optimism that goes into the plan in the first place. The reason somebody said go, the reason somebody wrote the check to run the trial was because they were presented with a perhaps overly optimistic viewpoint. One of the things I think, and this is standard in many of the forecasting platforms that are out there, is some appreciation of what the uncertainty is. What is that? When we talk about whether the hurricane is going to hit Atlanta or not, there's some zone of sort of confidence that about what that hurricane track is going to look like over time. And so too with enrollment forecasts. We need to sort of embrace that uncertainty, if you will. And yes, we're going to have some particular milestone dates that, yes, we expect to, on average, if we were to repeat this trial 1,000 times, we would not expect it to end on the exact, start on the same day or end on the exact same day each of those 1,000 times. There's going to be some wiggle room. And what does that wiggle room look like? And that's really, when we talk about kind of optimizing trials or making that plan, better. You can make it better by making it faster. You can make it better by making it cheaper, but you can also make it better by making your confidence intervals smaller, by essentially saying, the amount of risk that we're going in with this particular plan could be minimized if we do these particular things. And again, this, not to blow the trumpet too hard, but causal AI gives us this more kind of calibrated, rigorous understanding of, if I make this change, if I add these countries, if I add these sites, if I, engage in this particular marketing campaign, if I engage with this particular, recruitment vendor, these are the sort of expectations that we might have, not just about the average outcome, because really you're not going to run that trial 100 times. You're going to run it once. And so the average outcome isn't necessarily the thing that you care about. What you care about is your sort of, what's my risk of the worst case, which is, being 6 months late or 12 months late or 18 months late. And what is the cost of that, right? What if my trial came in 18 months late? What does that mean from a cost perspective, from an opportunity perspective, from a net present value of the asset? Those are things that considerations that once you kind of put that back into the mix and do that back calculation, you might say, okay, now, $5 million for that particular choice, whatever that is, totally justify it, because now, because my sort of risk of losing the NPV on that 18-month delay is far outweighs that particular cost.
Aaron, you don't know how bad I want to put a trumpet sound when you said not to sound the trumpet, and then but like like something like yeah, exactly. I have one last question for both of you, and we'll kick it just because you were just talking, Aaron. We'll kick it over to Jonathan, and then we'll give you last comment. So this is where we pull out our crystal balls here. This is people's favorite part, looking out. This is the part where no matter how specific you get, it's very likely that it could be wrong, right? And that is totally fine. Looking out 2 or 3 years, what will a clinical trial look like with the addition of causal AI technology? And how far away are we from leveraging this form of AI in the mainstream?
I think the clinical trial will provide a lot more data-driven decisions, because I think where we stand right now is we try to show up and say, okay, here's some nice examples of data that we have. And as data scientists, we will build Shapley plots of these very nice, beautiful plots that we say, this is the reason why we think X, Y, and Z. And we have certain packages called Lime, which help us understand, oh, we think this feature and that feature with all of these numbers. The reality is, I think if we can step back and show in a much more visual approach, like, hey, we see this and this and this, and they're related because of this big factor. And I think a lot of people will go, this makes so much sense to us. And I think providing like the explainable AI on top of what we're doing will really bring a big value. And I think for me, what I see on the day to day with study teams and kind of other groups is generally, hey, how can you really be sure about this? So I think that will actually give us, as data-driven strategists or scientists, citizen scientists, will be able to really drive a much more clearer understanding of what we're doing. One thing that I would like to add in, just from a crystal ball perspective, because I have the chance, is I think a big place where this is going to play a massive role, not just in clinical trials, but actually looking at drug repurposing as well, right? Because if you think about using all these other data, so we'll see in one trial, hey, we see this effect. But then when, as Aaron mentioned about net present value for other compounds, how does that spread across a multitude of portfolios, within a company? So I think that's where we're going to see the biggest impact. In terms of time, I'd say probably the next 3 years or so is where we'll start to see it. I think it's going to take about 18 months for us to get our heads around it, to also understand kind of the pitfalls, because we don't fully know them yet. We have ideas and we see initial excitement, just like Gen AI, and a lot of initial excitement. But until we can really show that value, that, hey, this is making a difference, and we can see the impact. And think about, studies can take up to 18 months before we get full readouts, right? So applying this and then seeing the readout, I'd say within about 3 years is when we'll start to have a much more business as usual application of causal AI.
I think that's right. I think the 2 to 3 years time frame is, as Jonathan, that's when we will begin to see the effects of it. It won't be a done deal. It won't be, that it's sort of, common operation everywhere. But I think it will be where, within 3 years we're going to see kind of rapid adoption of, teams that, haven't been using causal AI in the past, that will now start to, because there's been and again, it's the whole ecosystem, right? It's not one particular tool, it's not one particular method. Again, just like Chat GPT, we're still seeing how that is kind of working its way into our workflows and our tools everywhere, from email to supply chain to logistics to document handling and etc. So that story continues to evolve. I think this story will continue to evolve as well. The other thing I'd say, as a sort of certified old fart in this field, that if we were having this conversation 10 years ago, I'd be excited about the new advances that were happening 10 years ago. And 10 years from now, hopefully I'll also be excited about the new advances that are going to start happening 10 years from now. So at any point in time, I don't think we're at any particularly special point in time. We're just at another point in time. And I think there will continue to be new advances. Science has always been data driven from the beginning of time. So this idea that we have, I used to quip when the world invented the term data science, I said, well, as opposed to the other kind of science where we didn't use data, right? All science is data driven. We will continue to have more and more digital data at greater levels of resolution and greater amplitude, and continue to sort of push the boundaries of what we can understand. And the fact is, no matter how much data we have, we will still be missing something. We will always be missing. There will always be something hidden that we won't have opportunity for. And this is actually why I'm kind of excited about causal methods and how they are really becoming more mainstream. I mean, again, causal AI, causal stats have been around for at least 50 some years, probably longer, depending on how you actually think about it and define it. So this is not an entirely new concept, but it is being newly applied, right? Newly applied, and of course the sort of modern advances in both data generation and data warehousing and modeling and AI have really sort of allow us to sort of bring it to the forefront.
Well, I appreciate you guys shedding some light on what the future holds. I think, 10 years from now, it won't even be the three of us on this. It'll be our AI clones that know our answers and are having conversations with one another. And then we'll get an email about what happened, and hope our AI didn't say the wrong thing that gets us in trouble. Right.
Yeah, exactly.
Perfectly.
Thanks. Thank you so much for joining me here today. Look forward to future conversations, but appreciate you both shedding some light on causal AI, not casual, although I agree with both of you. Casual AI should be a thing somewhere. But thanks so much for joining us here today.
Thanks, Jerry.
Thank you.